Hi, so today we are going to be working on our electrostatic demos lab. It's a lot of fun. You get to see a lot of things that seem very magical to you because we really underestimate how strong electrical forces are. So in comparison to gravity and the formula for gravity, where G is a very small, big G in the formula is a very small number, and you need very big planetary size objects to really create a substantial amount of force of gravity. With electricity, it's the opposite. The constant in our formula in Coulomb's law is a very big number, so it takes a very small amount of charges to actually have a substantial or measurable amount of force. So that's what makes it pretty cool. And so even though we don't gather that much charge, we can get some really decent results today. So the first part of our lab, you were supposed to build an electroscope. Well, you can make an electroscope at home. All you need is a glass jar, some kind of a container. We used a rubber stopper here with a paper clip that is run through the rubber stopper. We have a ball of foil that's supposed to be a ball. It's supposed to be smooth. It is not. And then we have two foil leaves. So we cut little strips of aluminum foil, tried to make them smooth. They should be a little smoother than what's in here, but I'm not messing with it. Sometimes electricity can be tricky and like things work or don't work, and so I'm leaving it alone. It is June in Michigan right now, and this is not a great time to do a static electricity lab. I love doing a static in the middle of winter where it's nice, the air is dry. Why do we want the air dry? Because the whole point of static electricity is to build up charge. Well, you can't build up charge when something is leaking or siphoning off all the charges, and that would be the moisture in the air. The humidity in the air is a pathway for electrons to jump and abandon the large static charge and fly off. And so it is really hard to build up static in humid conditions. And that's why normally we don't worry about it. We worry about static electricity in winter, cold, dry conditions. Okay, so the first part of this lab, you are going to have your electroscope here. There are problems. There's an interaction sometimes with the glass in the jar, and I tried not using the glass jar, but that was another problem. So we're going to kind of have to just do the best we can with this, but we definitely can get some results here. So I'm going to move this a bit closer so maybe you can see the leaves a little bit better that are in there. And there are two. I'll move it so you can see them in there. And it says to take wool and PVC. So PVC, polyvinyl chloride, this is a plastic that is used in plumbing because it can hold high amounts of pressure, and it's easy to work with. And instead of wool, I know some people are sad, but I have a rabbit pelt here. And the reason is because it works the best. All right, it has, I don't know what it is about the hairs, but any hair will work. You can rub a piece of plastic on your own hair, but rabbit fur really does work well. They are very opposite on what's called the triboelectric series. The plastic really wants electrons, and the wool or fur is very willing to give up electrons. So when I rub these together, I end up rubbing electrons off of the fur onto the PVC rod. So this is getting excess electrons, and the fur is losing electrons. Now, if you lose electrons, so imagine all the atoms originally in the fur had as many pluses as minuses, and many protons in the nucleus as electrons on the outside, but now we remove some of those electrons. That means there's an overall positive charge here. While here on the PVC pipe, there's extra electrons, so it's going to have a negative charge. If I rub real well, it's not a little bit, I can hear some static ticking noises, okay? Like when you take off a wool sweater in winter, okay? And I'm hopefully gonna be able to make some happen. So I'm gonna bring it close to my ball. Oh yeah, did you see? Did you see that? Bring it close, they separate. Take it away, they went back, okay? So what's going on here? We know this rod is negative. When I bring it close here, what about the negatives that are in this ball of foil? Do they like negatives? No. So those negatives here say, I hate you negatives, and they run away, and they run as far away as they can. And far away as they can are to those leaves that are in there, right? And so there's an excess of electrons that have built up in the leaves because they've been chased away by the electrons in my rod. That leaves the ball here in a deficit of electrons. So this should have a slightly positive charge while the leaves have a negative charge. Well, both leaves have a negative charge. So the negative hates negatives, and what do? They repel. And they even are opposing then, I know force of gravity is trying to pull them down, but there's enough electric force of repulsion that they are defying gravity to somewhat. Okay? All right. Why does it go away again when I remove the rod? Well, this was induction. So this rod was no longer there. So the electrons say the coast is clear, and there's positives up here, right? And so the electrons go meet their positives and become neutral again, and everything is neutral. All right? I never transferred electrons there. All right? All we did was shift them from one place to another place because of the threat here in this rod. Okay. Now the next part, which is a little skeptical whether it never seems to work real great in the lab, but I have a piece of silk and I have a glass rod, and when I rub these two, they're very different on the triboelectric series, is that when I rub these two, I am rubbing the electrons off of the glass. Imagine that. I'm rubbing electrons off the glass and depositing it on the silk, because the silk kind of loves those electrons, okay? And the glass not so much. And so here I do this, so I'm going to rub more vigorously. And what's the charge going to be on the glass rod? Well, glass, when it's rubbed, it's kind of, remember, plastic gets negative, glass gets positive. All right? So what do you think should happen? The opposite? Well, let's find out. Let's see. Did you see? Could you see well enough? Those leaves still moved apart. Did you see it? You go, how come the same thing happens? How come the same thing happens if I have the opposite charge? Because the same kind of induction happens. So if I bring this rod close, what do we get? These are now positives in the rod. What about the electrons? Do electrons like the positive? Yeah. Remember, it's only electrons that move. So electrons run from everywhere and run and go, ooh, we want to see you, positive rod. And when they do that, all right, so what happens? Now the ball, right, as these negatives run up, the ball becomes negative, and you have removed, or you have a deficiency of electrons now on the leaves. So what does that make the leaves? Okay, and both those leaves are going to have the same charge, and no matter, same charges always repel, and so they separate. And when I remove the threat of the charged glass rod, right, everything here returns back to being neutral. Okay. All right. Next, what do we have? This now it says, take my PVC again and rub it with my fur or wool, whatever you have on hand. And it says this time touch the top. So I'm going to touch it up. Not only am I going to touch the top, I think I'm going to try to scrape some electrons off. Okay, like a knife with peanut butter that you had some extra and you want to get back in the jar. Same thing here. I'm not only going to touch the top, and I heard a little tick, I'm going to try to swipe those electrons off. All right, and can you, it's not perfect, but can you see that they're still apart? Okay, it's really, there we go. That's a better angle. You can see. Can you see those leaves are still apart? Okay. Because I transferred it a little more, didn't want to stay completely. Now it went away. See, the problem is they touched the glass, and I think it gave some of its charge to the glass. I don't have the most perfect container, okay? So they should remain apart, but again, I think it's touching. I'm trying to see if I can't get it to stay because it seems to be moving. It should stay. So when I touch the top, okay, when I touch the top, it should be transferring electrons in here. So now everything is negative. And when I let go, everything is still negative. So the leaves should stay apart. It's just a little bit of the problem with that. It's transferring it then to the glass, and I'm getting a little bit of a loss there. So once I touch those, everything becomes negative. transfer of electrons, and there's nothing, until it leaks away, which it did a little bit from the glass, they should remain apart. Okay? All right, so that's conduction versus induction. Okay. Oh, when these leaves are apart, and I don't know, I'm wondering if I can even do it. Hold on. I'm wondering if I can prevent the problem by taking it out of the container and then touching it. Let's see. Again, this time of year is not helping us at all. Okay. Okay, can you see they're staying apart now? Yeah? There's nowhere for those electrons to go. Okay. All right, conduction. Now, I'm going to try to touch the top, but the problem is I'm already pretty staticky. Oh, did you see it did work? Yay. Did you see they came back together? Because I touched the top, so I, was conducting to them. So the electrons jumped off because it was much more concentrated here into my very big body. Not only my very big body, maybe out my feet to the, what's the word, right? What's the word when all the charge can freely flow into a large reservoir? There's a word for that. I'm not going to tell you. You have to look in your notes. Okay. All right. Okay. So for our second thing, so we have our fluorescent tube. I have my PVC pipe with my fur again, and I'm making it have a negative charge. And I have an assistant holding on to a shorter fluorescent tube, and I am going to try to transfer electrons to the top. All right, my assistant is also holding onto the sink, and you should know the reason for that. And hopefully we get something to happen. All right, did you see that? So it's lighting up. Let me do it again. All right, so what do we know? Where are these electrons going? Are they just going into the fluorescent tube? Why is she holding on to the sink? That's to be a ground, and so the electrons are being transferred from my negative PVC pipe right through, and then it's exciting electrons in that rod. Now she's going to try to move her hand up. So her hand is now halfway up the tube. What do you think is going to happen now? All right, where are these electrons going to go? What's their goal, right? Aren't they trying to run away? So let's see what happens this time. All right, do you see where it go? Now do they run to the hand and stop? And notice they're not going all the way to the end of the tube. And so they're running through her to the ground. So they only lit up there. And if she moves her hand a little more, one more time. All right. And we can see again, it's only lighting up that section because we know the electrons must be traveling down her. All right. Thank you. All right, so now we are at table 3. All right, titled Dancing Hello Kitty. But Hello Kitty's got a friend. She's got SpongeBob with her. All I've done is set up 2 textbooks, a sheet of plexiglass. And this is plexiglass. What do you think it is made out of? Do you think it's made out of glass? No, it's plastic. All right, so it's a piece of plastic. I have a sheet of paper under here. And then I have my cutout friends. So I have a few versions of Hello Kitty and SpongeBob, and we are going to hope something works here today. Okay, this one can be a little bit finicky, but when you get a good result, it's really good. So we're back to rubbing my fur against my PVC. Oh no, I don't need the PVC pipe. I'm just going to rub the fur right on this plexiglass. So I'm going to rub here vigorously, and again create a charge situation where the fur is going to be donating to the plexiglass. Oh, there we go. They started to dance. Again, it is summer. It's very hard to get a lot of static. All right. Normally they would stay, but you can tell there's a great loss, okay, and leakage due to the humidity. Normally they would stay twirling. They're making me work. All right. Okay. So I'm creating break dancing Hello Kitty. She's dancing on her head for a while. Okay. All right. So that's the little demo there. You have to label the diagram, what the charge on the plexiglass is. Draw in, you don't have to draw a necessary SpongeBob. SpongeBob's probably easier than Hello Kitty. Just draw a rectangle or whatever. And then label charges on it. And this is a case of induction here, okay? All right. And the big question is always with Hello Kitty, like, all right, if she gets an induced charge, all right, if this is negative, she is neutral to start off with, but then the electrons want to escape from this. So there's electrons at her feet, positive charge at her head. So, and that's attracted, but isn't the charge a positive just as much as the negative on our feet? So why isn't this attraction the same as the repulsion, right? Shouldn't she be just as repelled as attracted if the charges are the same? Well, the charges are the same, but we had something else that was part of that formula, and that was distance, right? Didn't distance matter? What can you tell about the negative and negative, all right, and how much force that would be compared to the positive in her head to the negative on that sheet, all right? So you should be able to relate with Coulomb's law why she's more attracted than she is repelled. Okay, all right. Now we have our sink running. I'm trying to create a laminar flow where it's just a smooth flow. And I'm off here rubbing my PVC pipe with my fur again. And we're going to see if I can have some kind of impact on water here. All right, let's see what we get. Change my camera angle here. All right, you see that? I'm going to try to get a little bit more charge going here. Hold on. All right, can you see that? Can you see that water stream bend? Okay, can you see it's bending toward it? It's in fact spitting more of that water out towards that. Yeah? Okay, so I can even bend water with electricity. All right, so what's going on here, right? So what do we have? What's up with the water? So water, remember, H2O molecule. You learn in chemistry about water, and water is a Mickey Mouse shaped molecule, right? It is a bent shaped molecule where the hydrogens have a slightly positive charge and the oxygen is slightly negative charge. So it's polar. It has a positive end and a negative end. So if I bring something like a negative rod close, what do you think? How do you think those water molecules are going to orient? If this is negative, right? They're going to rotate. Are they going to rotate so the negative side is closer to my negative or the positive side? They're going to rotate so the positive side is attracted and the negative side that repelled moves away. It's very much like if you have a magnet and you bring it close to a loose magnet, doesn't it automatically turn around and then attract, right? You go again, isn't it as repelled as it is attracted? Yeah, but if it flips so that one side is closer than the other, then it's going to be more attracted than it is repelled. And that's exactly what happens here. Imagine that water is a bunch of magnets with a positive and negative end, and our PVC pipe is negative. All of the molecules will rotate such that they are attracted, okay? All right, in my desperation to try to find a place that has lower humidity to make our lab work, I am now in the biostorage closet, hoping that there was less airflow and less, I'm in June humid air in here, and it's working a little bit better. So here I have a Cheerio suspended by a string, just a piece of thread. So you can do this at home. You can use PVC pipe if you have it, or you can use a comb or a plastic ruler and a piece of wool, a wool sweater. And you can rub it together, and let's see what we get here. All right, so did you see that attraction? Now, if I'm really good and I can chase some of these electrons off, first you should get an attraction, but the leakage is still a problem here. You should get an attraction, and then it should repel. We do see that now. Do you see it repelling? But I think it loses its, oh, there we go. Did you see that jump? Oh, it is. So if this rod is negative and the Cheerio is negative, becomes negative by conduction, right? First it's induction, it's attracted, then the electron should transfer, then they should both be negative, and then they should repel. And we can kind of see, but it's a struggle here. Okay, now we can see some, well, but not as perfect as we would like. Okay, there we go. That was some good results from that.